So we can convert grams of, in this case, A, some kind of A, so we can consider this hydrogen, convert to number of moles of hydrogen, right? And from moles of hydrogen, we can find, say, moles of ammonia. Say this B is ammonia, right? And then from number of moles of ammonia, we can find the grams of ammonia. So this also helps if you know chemical reaction, you know how to convert, how to connect all these things, so you can just easily find out how much product you can produce during chemical reaction. Now let's just, so this is basically the same scheme, mass of compound A. You can go to, it says over here, use molar mass, gram per mole of compound A to find moles of compound A. Then from here, you can use molar ratio of the reaction, right? You can use molar ratio of the reaction. And from here, you can find moles of B. So from moles of A, you can find moles of B. Once you find moles of B, again, you use molar mass, which is gram per mole, right? You can find mass of B. Now, let's look at this picture over here. And let's consider it, say, this is A. This red ball is A, and this blue ball is B. Can you suggest the process which you see here on this picture? Can you write it down using A and B? Think a little bit and then let's discuss. Okay, let's see. I want to see like the whole process, not only like left-hand side, but also right-hand side. So you need to describe the whole process in terms of A and B.
Can we say A plus A gives B?
Well, no, you have here. Okay, so let me explain again. So in this part, you have A's and B.
Sorry, doctor.
Yeah.
We can say 1 mole of B2 and 2 mole of A. That they can combine with each other.
Yes, that's true. That's true. So, but can you just, yeah, this is the right way to go, but you need to consider all of these balls, all of them. I understand what you say. Yeah, eventually it's going to be like that, but please consider all of them and include all these balls in your equation. So we need to write equation like A plus B is whatever. Okay, so but you need to put some coefficients in there, so in order to make it looks like a reaction. Okay, so if it looks like reaction like this one, but you can express it in terms of A and B. All right, so how many A's you have on the left hand side?
8.
8. Okay, let's just write 8 A. What about B?
Also 8.
Okay, also 8. You say you have 8B, right? You want to write it like this way?
No.
Okay, so how?
We can write down 1, 2, 3, 4, 4b2.
Okay, 4b2. And what is the result?
Result is
For
4
A2,
4 b2 plus 2a.
Plus 2a?
2a. I mean 4 4 is for both of the a and b. I mean 8a2 we can write 8a2.
Okay, let me write it and then let's just see. I think somebody said that. Okay, so you write 4,
yes, doctor, I said for A2, B2.
yeah, 4a2b2.
Yes.
Now let's just check. Now let's just check. How many a's you have on the right hand side, left hand side?
How many what?
A's. So how many is here?
8.
8.
You consider all the balls, it will
So
be 8
okay,
for left hand
okay.
side.
Yeah, so we are now looking at the equation. Forget about balls, we're now looking at equation.
Yes.
So we have 8 A's, right? So what about B's? How many B's we had?
8.
8. Now, so we used 8 A's, we used 8 B's. Now let's look at the right hand side. How many A's we had?
Oh,
8.
8. What about B's?
8.
8. Okay, so everything is right. So we have exactly the same amount of A's on the right hand side and left hand side, the same about B's. Now, why we write like A2, B2? So this is like a, so I said that this is B. So this is B. So it means that if they are two together, it means that this is B2. So we have only 4 of these B2s. So this is why we wrote 4 B2s. But A's are independently, like 1, 2, 3, 4, separately, right? This is why we write 8 A's. Here, so we have this kind of unit, okay? So this unit, you mostly will think that this is either A, B2, A, or simply you can say A2, B2, right? That's the same thing. So how many you have this one? 4. So this is why we wrote like for A2, B2. So this is just a mimic of equation. What I want to say by this is that you take whatever amount you take on the right or left hand side, you need to end up with exactly the same amount on the right hand side. Yes, you can rearrange these components. This is why we have chemical equation. You can rearrange it, but it should be the same, exactly the same amount of the components. Okay, so this is basically what is happening during chemical reaction. We need to consider this. I'm sorry, do we need to have next? That's clear, right? This is about limiting reagent. Maybe if you watch the, I want to go through this just to make sure that we understand everything what was uploaded. This is about limiting reagent. If I tell you that, yeah, it talks about hemoglobin, right? So say if there is a lack of iron, because hemoglobin contains iron in the middle, it's an enzyme protein, so globular protein, so it has iron in there. You will study it in biochemistry. But if there is not enough iron, so then the hemoglobin is low. Why? Because in order to have right hemoglobin, you need to bind. It needs to bind oxygen. Then oxygen needs to be delivered to the system of the body. Okay. So if you do not have enough iron, you cannot bind oxygen enough. So then the system is kind of screwed up. Or by the way, it can be opposite way as well. So if you do not have enough oxygen, then again the same thing will happen. So in this case, so it means that iron is a limiting reagent. Okay. And by the way, there was a study I can tell you that two groups of people who had both of these groups had anemia, and they were fed from the pots made. One of the group, we are kind of given the food from the pots, which was made from iron, but the other one was given a food which was made in the aluminum pot. Okay, and the first one actually they found that for the first one anemia was gone at some point because they during cooking some iron goes to the food. Okay, of course very small amount because when there is a cooking going on, they are quite severe environment because it's hot, you know, and there is also some maybe acids coming out which can oxidize the iron pot, and some ions of iron can go to the organism during the like feeding and together with food. So yeah, so again, limiting reagent is the one which basically determines the rate of reaction. Okay, for example, say you are making the hamburger. Let's see like that way. Say you are making hamburger. So you have bread, you have meat, you have cheese, and you have salad. You have two breads. Now let's see like you have like 4 breads. You want to make like, you have 4 breads, right? You have say 2 meat. This is meat. You have 2 cheese, and you have 2 salad. So how many hamburgers you can make? Say hamburger like
Two.
yeah,
hamburgers.
exactly, like the say this is the hamburger, right? So this is hamburger. So how many like this one can you make? Like this hamburger, how many of them you can make?
Two.
2. Okay, true. You can make 2 hamburgers. Now imagine, then you lost one of the bread. Okay, now you have not 4 but 3. Okay, how many hamburgers you can make?
One.
Just
One.
one. Exactly. Why? Because you do not have enough bread. Okay, so you have like lack of bread. So everything depends now on bread. You have extra cheese, extra meat, extra cheese, extra salad, but you do not have enough bread. So limiting here is bread, right? So once you are ended up with like, once you consume the bread, you stop, you cannot make any more, but you have extra salad, as extra meat and so on. So the same thing is in chemical reaction. So say you're having reagents at the beginning, but one of them is small amount. So once you consume everything from that small amount, then the reaction stops. Okay, so that's the limiting reagent. But another one, which basically in our case, it's like meat, cheese, so on, that's the excess reagent. Okay, so that's the excess reagent. So this is about limiting reagent. Another thing which is very important, by the way, very important. I want you to pay attention to this, because these kind of things we will have in exam. Okay, this is reaction yield. If we go back, say, if we go back to our hamburger, okay, tell me how many hamburgers you wanted to make at the beginning before you dropped one of them.
200.
Two.
You wanted to make 2, right? So this was like theoretical intention. So you wanted to make one for you, one for your friend, okay, or both of them for you. I don't know, doesn't matter. Theoretical. Theoretical. That's the theoretical, your thoughts, right? You wanted to make 2, but suddenly you dropped 1, and one bread. You dropped one bread and you made one, right? So that's the practical, which means actual. Practical,
Yeah.
or this is actual. Okay. Can you tell me, so what is the performance? What is the, in terms of percentage? What is your performance in terms of percentage?
50%?
Yeah, so it's a 50%. Yeah, so your performance is just 50%. How did you find it?
Because the actual and theoretical is got a half.
Right. So you, what you do is that you divide actual, so 1, which is actual, right? You divide it by 2, which is theoretical, right? So it gives you, and you multiplied it, let's just already multiply. So, and you multiply it by 100%, right? So it's going to be 0.5 by 100%. So eventually it's 50%. Okay, is that clear? So this is actually what is reaction yield, and this is how it is calculated. So you have actual yield, you have theoretical yield, and you multiply by 100 and you will get percent yield. So how you need to find theoretical or actual yield? So you need to look at the equation. All right, so you need to look at the equation. Okay, and first of all, you need to balance the equation, make sure that it's right, and so on. Okay, and according the reaction which is written on the paper, okay, you just write it on the paper. This is what is the law, this is what is the rule tells you, that to write the reaction like that way. And then according the reaction which is written on the paper, you need to find amount of products which can be generated from reagents. So in this particular case, it was found that the theoretical amount of titanium solid, because titanium is, by the way, very widely used in medicine. It's artificial joints are made of titanium, and because it's very stable against corrosion, and it's very widely used in medicine. So say you are producing titanium, and you are a producer, so you don't want to lose a lot of titanium, because basically you are losing money, right? And you need to consider what is the outcome of your production to know how successful you are. So in this particular case, it was found that theoretically, it was calculated that according this reaction and according conditions you had, you needed to produce this amount of titanium. But for some reasons, it was not produced, and actual production was just this amount. So the yield, percent yield, was found that it's 83.1%. So usually there are many
Doctor,
reasons. Yes.
how we can know the number of actual and theoretical?
So actually, you just measure it. Say you just weight it, for example. So you just collect this titanium and then you weight it. That's okay. I mean, that's not a problem. You can just find the mass of this one by just practically how it is, because there are some balances which are really special for that. So you can just weight it, or special approaches to weight big amount of the product, maybe other ways as well. But theoretical is calculated. So you need to calculate the theoretical. I think I should have, maybe not, but you need to calculate the theoretical yield. I think we should have some, let me see if I have some examples of that. Okay, maybe next time I'll bring these slides which we have. For example, since you're asking, let's just check how we can calculate that one. Let's just take very, very simple example. So it's easy to calculate. Say you have carbon, you oxidize carbon, and you are getting carbon dioxide. Okay, so is this reaction balanced? It is, right? Let's just take a reaction which is not balanced because it's too easy. So let's just take carbon and you make carbon monoxide, not carbon dioxide, but carbon monoxide. You also can make carbon monoxide. Let's just balance it because you cannot leave it reaction without balancing. Let's just balance it. So how we balance it? So we have two oxygens here, just only one oxygen here. So we need to put two over here, right? So now we have two carbons here, but only one carbon here. So we need to put two carbons here, okay? Now, can you tell me, according this reaction, how many moles of carbon is used, how many moles of oxygen is used, and how many moles of carbon monoxide is produced?
2 moles.
2 mole of carbon and 1 mole of O2.
Exactly. So we have 2 moles of carbon, we have 1 mole of oxygen, and we have 2 moles of carbon monoxide. Exactly. So this is what is the in terms of moles, right? Now let's just see if I take, imagine that we had at the beginning, we had 24 let me see. Okay. Let me just give you some numbers. Say we have 24 grams of carbon from the very beginning. So we know we measured the carbon at the very beginning because before starting the reaction, we measured the carbon on balance. For example, we took 24 grams. How much carbon monoxide we should produce?
24.
Why?
48. 48.
How did you find this 48?
You said 1 mole of carbon has 25 grams, yes?
No, 1 mole of carbon is 12 grams. 1 mole of carbon is 12 grams, okay? 1 mole of oxygen, 1 mole of oxygen. So this is carbon, this is oxygen, it's 16 grams. Okay, so what do you need to know from the very beginning is that according this reaction, it means that 24 grams of carbon, because we have 2 moles of that, right?
Right.
So it means that how many grams of carbons we have?
24.
24. So it means that 2 moles of carbon produces 2 moles of carbon monoxide, right? This is what we know from the equation, okay? Which means that 24 grams of carbon produces how much grams of carbon monoxide?
56.
Okay, let's see. So we need to combine 12 and 16. It's going to be 28. 28 by 2, it's going to be 56. That's correct. So it's going to be 56. So 24 grams produces 56 grams of carbon monoxide. Okay. In another word, the same thing, you can say that 12 grams produces how much?
2.
No, why 2? Look, so 24 grams is 2 moles of carbon.
44.
Why 44? No. Okay, look. 24 produces 56. Right now I'm taking 12, which is 2 times less than 24. How much carbon monoxide? 28, of course, it's going to produce 28, twice less than 56, right? You just make a ratios. Now, say I took not 24, not 12, but say I took 32 grams of carbon. Can you tell me how much carbon monoxide can be produced?
$74, I think.
Yes, it's kind of close. Let's see. It's going to be X grams, right? So we need to find X. How we find X? We can cross multiply this by this, and then
84.
Yeah, so then maybe 84, I don't know. We need to, okay, multiply 32 by 56 and then divide by 24. So this is how you make it, okay? So you multiply these two and these two, cross multiplication, just very simple operation. And you find X. So what's going to be the X?
84.
84. X is 56 times 32 divided by 24, which is, say it again, please.
84.
84 grams, okay? So this is what is theoretically supposed to be produced if you take 32 grams of carbon. So this is what is supposed to be produced theoretically. So this is carbon monoxide produced, okay? Now imagine, so we made a reaction, but we found that we could make only 78 grams. That's the actual amount of carbon monoxide we produced, 78 grams. Can you tell me now how to find out the percent yield of this production of carbon monoxide?
Can you repeat, please, Doctor?
So the question is that I have actual yield is 78 grams, okay? Actual yield. This is the theoretical yield. Now I want to see what is the percent yield. Just recall what we discussed about hamburgers. This is actual, this is theoretical. So the same approach as for hamburgers.
%92%.
Yes, looks like that. So it's gonna be percent yield.
0.92.
No, it cannot be 0.90. So percent yield is gonna be actual, which is 78 grams over 84 grams multiplied by 100%. Divide 78 by 84.
0.92.
0.92.
0.92 and then multiply it by 100%. It's gonna be 92%. So that's the percent yield of the production of carbon monoxide, okay? So you might think that why it's important. So you guys want to be dentists, right? I mean, I don't know, maybe you Well, we don't know, but you try. So since you are on dentistry program, so you want to be a dentist, right? So then you are making some artificial jaws from the polymer. Okay, so you have polymer, you want to make it, and then you're supposed to have, say, from 2 kilos of polymer, you need to make like 3 jaws. I mean, I'm just saying, just for example, but you could not make it. So you could make like 2 only, right? So you need to think what is the percent yield of your production. So this is very important parameter to know, not only for like production industrialists or technologists, for for people like you who are working in the say if you go to pharmaceutical industry, right? So you change your profile and you go to pharmaceutical industry, you need to know this one very, very precisely. What is the percent yield of your production? Because this is the money, okay? So you cannot like use a lot of chemicals and just end it with just very small amounts. So you have to produce as close as possible to the theoretical calculations. It's not possible usually. It's not that easy, but you have to try to make it as close as possible to the theoretical. So how you can make it, you have to consider each and every detail, every step very carefully, and be very careful during the production in order to not to waste the reagent, okay? So this is why we need to know what is the percent yield. Okay, so this is clear. So mixture solutions, I think you can just find it out yourself. Also matter, we also discussed about this one. So if you can decompose something, then it's going to be mixture, right? If not, it's kind of pure substance. Then mixtures can be heterogeneous and homogeneous, because you might see sometimes that you have particles in the solution, right? So that is not homogeneous, that is heterogeneous. So you have homogeneous solutions as colloids. So for example, milk is like more colloids, okay? And it depends on the particle size. I think I should have, yeah, here. So it depends on the particle size. Solution, when you have particles less than 2 nanometer, so it can be colloids. So air, seawater, gasoline, wine, right? So if it is between 2 and 50 nanometer particles, it's like more colloid. So like milk and so on. So heterogeneous is like when you have particles more than 500 nanometers, for example, blood, okay? Because there are some proteins, say, or some macromolecules which are really, really big. This is solution process. So how we make these colloid solutions and heterogeneous systems or homogeneous? We dissolve something in a solvent, right? So, for example, blood is a solution, because we have, even though we have some big particles there, you also can consider it as a solution, because if you just purify it, it's just solution. And so what is the solvent? It's water. So water is a solvent, and there's many things dissolved in there. So you have solvent, you have solute, and there should be some interaction between solvent and solute to make the solution, right? So they should like each other and so on. So everything has solubility. You cannot dissolve more than it can be dissolved. For example, if you put some salt in your soup, okay, you can dissolve it. But if you put like the whole box of salt in your soup, of plate of the soup, you will not be able to dissolve it, because there is a room which cannot like put more than that. So imagine it the same thing, that people are on the bus and it's packed. You cannot put more, right? Because you cannot close the door or anything like this. But if there's not much people, yeah, so you can just walk on that. So the same thing is here. So you can put particular amount of solute, and you cannot put more than that. Every solute has ability to be dissolved and be soluble. So solubility is very important, because and it depends on, so this is just which one is soluble, which is not soluble. For example, this is the reaction, how to find out if there is a silver in a solution. So say you have solution and there is silver ions in there, so you can make reaction like this and silver will be just identified. Okay, the solubility depends on many things, so you can just check it on. Okay, I have less than 1 minute, but let's just finish it, and then this is end of our class. Or you know what, let's just me, yeah, so basically there are many things to explain, so let's just finish here. So this is solubility. So for example, for gases, if you increase the temperature, the solubility decreases. So it's opposite, basically. For gases, you increase the temperature, solubility decreases. But for, say, sugar, for salts, it's opposite. So you increase temperature, it increases. So for example, if you put sugar in a tea, in a cold tea, it's difficult to dissolve it, right? But if you put sugar in a hot tea, then it's very easy to dissolve it. So it's two different things. For example, you have Coke. So for example, in the Coke, you can